In this example, we're told we have a large tank with some pressure and temperature conditions. By the way, this should be an absolute pressure. And we're told the tank feeds a converging diverging nozzle with the throat area, with a given area there. At a particular point in the nozzle, the Mach number is equal to 2. What's the area at that point, and what's the mass flow rate at that point? So that's what we're looking to find. So let me just sketch out the geometry. So we have a large tank with a converging, oops, that's drawn very poorly, with a converging diverging nozzle. Pressure here we're given. So when it says the large tank, that means it's at stagnation conditions. The velocity inside that tank is very small because it's such a large volume. The stagnation temperature is 27 degrees Celsius, but we should put everything in terms of absolute pressure and absolute temperature, since the compressible flow relations we use have been derived mainly from, well, at least in part from the ideal gas law. We need to use absolute pressures and absolute temperatures. So 27 degrees Celsius is 300 Kelvin. And we're told the tank feeds this converging diverging nozzle. The throat area is given here. So let's write that down. And then at a particular point in the nozzle, the Mach number is equal to 2. So that point's going to be somewhere downstream of that throat. So there the Mach number is equal to 2. Let's call it location 1. And the reason I know it's downstream of that throat is because the flow is starting from stagnation conditions and it's ending up at supersonic conditions. So the only way that can happen is if we go through a minimum area, which is the throat. And we know that since it goes from stagnation conditions to supersonic conditions, that minimum area will be at a Mach number of 1. So the Mach number at the throat is 1. And the area of the throat is also A star. Remember the asterisk here indicates that we're at sonic conditions. All right, so what's the area at this point 1? So the way we'll find that is we can use the isentropic sonic area ratio. It's this relation that looks like this. Let me just write it out and then we'll talk about it. This is one of the relations that was derived in the lecture notes or lecture video. Okay, so there we go. So what this relation gives you is if you're given the area at a particular Mach number, so in this case it's the area at 1 and the Mach number at 1. So we're talking about this location right here, that we have the Mach number at 1. We're trying to find the area at 1. So there's area 1, Mach number 1. And A star is the area of the throat. It's the area where we have sonic conditions. So we know A star, that's equal to the 6.45 times 10 to the minus 4 square meters. We know Mach number of 1, that's equal to 2. And then the K is the specific heat ratio for air, since we're dealing with air in this tank. That's 1.4. So we can solve that equation for A1. Comes out to be 1.09 times 10 to the minus 3 square meters. Okay, so that's part A of the problem. We're also asked to find the mass flow rate at that point. So there are two ways we can do this. One is to use the choked flow mass flow rate. Since we know the Mach number is 1 at the throat and it goes supersonic, we know that the flow through this converging diverging nozzle is choked. So we can use the choked flow mass flow rate. Let me write this one out. This is kind of a long relation. Okay, so that's the choked flow mass flow rate. That's the maximum mass flow rate you can achieve by lowering the back pressure. We know again K is 1.4. We know the gas constant for air, it's 287 joules per kilogram Kelvin. Those are good numbers to memorize because we use air very often in gas dynamics. P naught, we know that's the 0.7 times 10 to the 6th pascals absolute. We know T naught, that's the 300 Kelvin. These are the conditions in the tank. And we know A star is the area at the throat, since the throat's at a Mach number 1. So we have all this information, and so we can use it to solve for the mass flow rate. And that comes out to be 1.05 kilograms per second. It's the same mass flow rate through the entire nozzle, since it's a steady flow. Now, another way we could find the mass flow rate is just to find the mass flow rate at this vertical plane 1. So we could also do mass flow rate's density at 1 times V1 times A1. A1 we just solved for a little bit ago. That's right up here. The velocity at 1 is related to the Mach number at 1 and the speed of sound at 1. And the speed of sound at 1 is just the square root of kRt at 1. So the Mach number we know. Speed of sound, well, we know K, we know R. To find the temperature at 1, we can use our adiabatic relation T1 over T0. Looks like this. So we know T0, that's 300 Kelvin. We know Mach number at 1, so we can solve for T1. I didn't actually solve that number, but you get the idea. We can solve for T1. So that would give us the temperature at 1, which would then give us the speed of sound at 1, which would allow us to find V1. As far as finding the density at 1, we could use the isentropic relation, ρ1 over ρ0. Looks much the same as the temperature relation. I believe I've got that exponent correct. So this expression involving temperature is used for can be used for adiabatic conditions as well as isentropic conditions. This one can only be used for isentropic conditions, but that's fine. We'll make the assumption that we have isentropic flow through that nozzle. That's a pretty reasonable assumption. We know the Mach number at 1. The density at stagnation conditions we don't know, but we can find it using the ideal gas law. Since we know the pressure and temperature, we can find the density in stagnation conditions. So that will just be P0 over R T0. That's using the ideal gas law. So we should be able to find the stagnation density. Once we have that and the Mach number, we can solve for ρ1. So again, I didn't work those numbers out, but you get the idea. Now that we have the density at 1, we found the velocity at 1, and we have the area at 1, we can find the mass flow rate. When you plug those numbers in, they'll be the same as this. Okay, so that covers everything for this example, so we'll just go ahead and end it there.